right, so as I mentioned, my name is Kaylyn. I work at Capital One Labs, so I do a lot of API design, but mostly in prototyping phases and some elements of research. But over the past year, I kind of picked up a new hobby, which you might be able to guess has to do with algorithms. And it might be a little bit surprising because for a lot of you, when you see the word algorithms, you probably think something along these lines. I know I certainly do. Most conferences, when people start doing presentations on algorithms, I might break out in a cold sweat. I feel very inferior. I had a lot of history of just wow, these are the greatest people, they know so much. And essentially my history started and stopped in college, where I learned algorithms just well enough to get through programming interviews, and then I completely dropped that and moved on with my life and figured I would never come back to it. That was until about a year ago. I had kind of a bored weekend, and I started going through Coursera, and I was maybe I will try one of these classes. Maybe I'll give it a shot. And as I was going through, the classes were taught always in various other languages, like C++ or Python or Java. They never, ever were giving examples in Go, but I was writing them in Go, and what I found was that if you write the algorithms in Go, you actually have a better experience. So that is mostly what I'm here today to talk to you about. One, to explain why, and then two, to kind of give you some examples so that you can learn from it as well. The main premise and kind of what you would find if you're coming from other languages are that a lot of times there's a ton of data structures. So if you do your classes in C++, you're going to spend a lot of time understanding why are we using a linked list or a vector or a queue, and you put a ton of energy into it. So once you figure that out, then you have to understand the algorithm. Once you understand the algorithm, you're exhausted, so you no longer care if you have an optimized algorithm. You're this just runs, and that's all I need to know. And that's kind of problematic, but in Go, you don't have to do that. Not only is it simpler to write, but there's a ton of features in the language, like testing and benchmarking, that make it super easy for you to know if it works, and also how you can optimize it later. So in this talk, we're going to go through two different areas of algorithms. So there's sorting and there's searching. Specifically, we're going to look at quicksort, and then later we're going to touch on binary search to just show you how quickly you can start picking them up once you began. But before we start, I wanted to highlight a bit of who this is for. If you are new to Go, this would hopefully be really great for you to see these simple code examples that will walk you through these algorithms, and you'll be oh, I can pick this up having a C background. I can pick this up from other languages. It seems very familiar. Or maybe you are new to algorithms, or you've just blocked them out of your mind like I had for about 5 years. That's great too. Hopefully you can kind of see through the experience, this is what they're doing. We picked kind of some fundamental algorithms for you to follow along with. But the third group might be a bunch of you who are sitting here I already know Go. I could write Quicksort right now. Maybe that's exactly what you're doing on your computer. But even if that's what you're doing right now, I want you to I kind of want to propose to you that there could be some value in this talk as well, where you probably don't spend a lot of time explaining algorithms to other people. And there's around you a ton of newer developers or people who've just ignored them that would love to learn these algorithms from you. So as I go through, maybe this could be value, and I would love your feedback around can I then go teach this to the people around me as well. So without further ado, we're going to talk about sorting algorithms. The names sort of give away what they do, but a sorting algorithm, you take an unsorted list and you put it in order. I couldn't really talk about sorting algorithms without showing you this. It's kind of obligatory, but this is essentially giving you all the different runtimes of some of the most popular sorting algorithms. So they do them with different inputs. So there's random, there's something that's already almost sorted, there's something that's completely flipped, and you kind of get these disparaging times, and that's what tells you why you might want to use one algorithm over the other. We're going to look at quicksort. So quicksort, I have up here the literal textbook definition that comes out of the C programming language. This may or may not be fun for you to read. It certainly isn't for me. I fall asleep six words in. But for me, what quicksort actually means is it's essentially an algorithm. You have an unsorted array, and you're going to click one element that's your pivot. That number becomes really important because you're going to look at every other element in the array and do a comparison. If it is less than that number you've selected, you're going to keep it on the left. If it's greater than, you're going to keep it on the right, and you keep iterating on that until you've finished your algorithm. This turns it into what's called a divide and conquer algorithm, which sounds super aggressive of a term, and it certainly is. But essentially, it just means you're going to break down the problem into subproblems so that you have to spend less time on each one as you go. To make it clearer, though, I brought some friends with me. And we have a bunch of gophers that we're going to sort into an actually ordered list. How we are going to do that is what I mentioned. We have this first element that's our pivot. We're selecting the last one in our list, which is D. You can kind of eyeball this, and by glancing, you can see that B, A, C probably goes on the left, and GEF is going to go on the right, so we would end up with something like this. But how do we go about doing that programmatically? So the first thing is we start at the very beginning of the list at this B element. We need to start keeping track, though, what is going to be lower than come before D and what is going to come after it. We do that with a split variable. So every time we see an element that comes before D, we know that this should be on the left. And so in this case, since B is the first, we'll keep it right there. And we'll increment split. Split is going to tell us that everything to the left of split comes before D, and everything at split or after comes after. So we increment. We move on to G. G comes after D. So we're going to increment again. We don't have to do anything with split. A comes before D. So at this point, this is our first time that we're going to have to do a swap, because A should be before G in this list. So we swap these two elements, and then we increment split. Again, you can kind of follow along and see that B and A are now before the split variable, and G is starting everything that happens after. We move on to E, comes after D. Move on to F, comes after D. And then we get to C, and this is the last element, which happens to be before D. So we swap these two. We end up with our split being on the 4th position. And what that tells us when we get to the array is that's where we have that divide. That's where we have all the elements that are less than before that point. We can do the swap with D, and we have it in the final position. This D no longer needs to be moved. It no longer needs to be touched. It's completely finished. And we can start looking at this array in 2 separate parts. This is essentially the divide and conquer. Now we can do the left array and the right array. I'm going to run through these super quickly. It'll be about 30 seconds, but I do want to parse through it, because if you're looking at this for the first time, it can kind of be a little novel to grasp. So on the left side, we have our C as a pivot, and we're going to go through B. B comes before C, we increment split. A comes before C, we increment split. We end up at a point where split is at the pivot. What that means is that the pivot is swapping with itself. It's staying in the same spot, and it's done. We have this left array. A becomes our pivot. B comes after A. So now we know we need to swap these two. A is in the final spot. B is an element of 1, so we know that's final. And we've done this first half of the array. The right array is the same thing. They're a little bit different orders, so we'll pass through it pretty quickly. But E is our pivot point. F, we can see, comes after E. So we're going to increment again. G also comes after E, so split stays in that first position. And again, we swap them. Now we have these right array, 2 last elements. F becomes a pivot. G becomes what we compare it to. G comes after. We do this swap. F is in this final spot, and G is in the final spot. At this point, we now have our completely sorted array, which can be a little complicated if you're following along and feels pretty long. But fortunately, we don't have to do this by hand every time. We can actually start looking at the code that will do this for us. If you've looked at Quicksort in the past, hopefully this looks somewhat familiar, but essentially what is happening here is when we took our D at the very beginning and moved it into the middle where we had everything on the left less than and everything on the right, that's what's happening in this partition. This is a function that essentially does that for us. So the first thing we're selecting is pivot. We have pivot being our last element in the list. You could have your pivot be the first, you could have it be in the middle, but essentially you just need to select one. And then we start tracking our split variable. The next section has this range of nums. If you're new to Go, this is a really fun little thing that you can use. Instead of doing for I equals 0, I is less than the length of nums, I plus plus, you can just do this range, and this gives you both the index as well as the value in n. So you can use both of those to do the actual check around, is this less than or greater than your pivot value? The only check we have to do is if it's less than, we swap the 2 values, and then we increment split. We do that the whole way through the array until we get to the very end, do one final split swap of our pivot and the split point, and we're finished. The only thing I also wanted to mention, if you're coming from C++ or Java, I don't know why this was so delightful for me, but the one-line splits is just like a super happy thing. Every time I read in a textbook like C++ where they're like, we have a whole function for swap, I'm like, yes, we don't need that. So that's like a fun thing for me. After that, you might have noticed we weren't doing divide and conquering, we weren't doing the recursion. That's what we have here in Quicksort. So Quicksort is accepting an array of numbers, and it first checks to see if the numbers are less than or equal to 1, we know it's already sorted, we can just return it. After that point, we get the pivot position, and then we split the array into the left and right based on that pivot point. You might have noticed, or you might be questioning if you're newer to Go, everything is sent pass by value. So you might be wondering, why am I not returning the array of numbers at the end? That can be actually very confusing when you're testing out a bunch of algorithms if you don't understand what's going on here. But what's essentially happening is we are passing these arrays by value, but a Slice is a header that has a pointer to these arrays, and that's what will tell you, like, that's what's changing the arrays. So every time we have a call to Quicksort, we're essentially creating a new slice. These are different slices, but they are all pointing back to this underlying array, and every change that you make makes a change there, which is what shows over time, and you don't need to be returning it. I'm going to do another example of this in a second. But this is essentially the algorithm. You can sort of see it's relatively easy to follow along if you have some familiarity with programming languages, but this is not the only benefit that Go gives you while you're learning algorithms. The best part is when you start getting into testing. This is when you can feel really confident that what you're writing is doing what you expect it to do. So this is a pretty standard test. The only thing that is potentially not standard here is you can see at the very beginning of the for loop, we have this whole list of tests, and they could be running a sorted array, they could be running random amounts of arrays, and we're going to iterate through those and test them one at a time. But this line 10 and 11, what's happening here is that I'm copying the array that we're going to use as the input for Quicksort, and that means that we aren't going to change the underlying tests every time we run this. If we didn't do that copy, you would have what we kind of saw on Quicksort before, where the tests would get actually altered every time you were running them, which meant later on if you tried to use the same one, it would already be sorted and you wouldn't realize that your results are different. But aside from that, this is essentially the checks that you do. You can use reflection to compare between two different arrays and have your little test there. The other thing that I wanted to call out, so this is how you can do different tests, test tables. And so what you can see here is you have the input and the output. You can specify them by name for each value that you're creating, or you don't need to list out the name. You can just kind of go line by line. But this makes it very easy for you to create a lot of tests that you can throw at your algorithm to be like, OK, I'm feeling pretty confident this is doing what I'm doing. If you're doing online classes, you can just copy the tests that they give you and put them there, which is really nice. The next thing that's fun with algorithms is that we can do benchmarking in Go. And this is like, this just makes you feel super powerful. Because in a lot of other languages, you have to do like time.now, get that timestamp, run your code, and then figure out what happened at the end. And that's like very clunky, very not scientific. And depending on what you're running on your computer, you could get various results. So what's happening here in Go is that we have this whole benchmarking built right into the standard library. All you need to include is that b testing.b. What that's checking, so you have in every benchmark function, you have for I equals 0, I is less than b.n. b.n is essentially running loops until it starts to get a reliable result on your function, and it will return that to you what that speed is. So when you run Go testing with the bench flag, you're going to get these results. And what we're seeing right here is that it will run 10 million iterations of Quicksort at about 183 nanoseconds per operation. And if you're somebody like me, this is like super fun, because now you can go through and start saying, hey, do I need this split variable? Hey, what else can I optimize? And kind of get that number down. And it actually makes it enjoyable to learn like what the different optimizations are for the algorithms. I had one more thing that I wanted to bring up with benchmarking. If you wanted to run a bunch of benchmarks at once, so you might be saying, OK, I've ran it on, and the last slide I have about 10 items in there. I've ran it on these 10. What happens when it grows larger? What happens when I do different things with the array? You can do that as well. The best way to do that is by having a private function of benchmark, and this will accept the array that you're going to send to Quicksort, and you can then run that over and over and essentially create a long list of all of these benchmarks that you want to test. So you could have 5 elements, 10 elements, 20 elements. You can kind of see I incremented it here. And then when you run benchmark, you'll see the time difference, which is also a lot of fun. You get up from like 12 nanoseconds for just the partition all the way up to 57,000 nanoseconds when you're running 1,000. And you can really use this to analyze your code and see how this might compare with other algorithms. So I put 2 at the end of Quicksort when it's flipped and when it's sorted, and you can see the time's about the same. For other sorting algorithms like insertion sort, you would actually get very different answers there. If insertion sort is flipped, you're going to be much slower than a previously sorted array. And those are just kind of the nice features that you can pull out as you're programming these. OK, now we're on to the next section. And this one's a bit quicker because you've already learned the fundamentals for testing and benchmarking our algorithms in Go. This is the description from Geeks for Geeks, one of the super popular online resources for algorithms. But even though it wasn't written in the 80s, it's still kind of dry to read. And essentially what binary search is it's similar to Quicksort in that you have your array, it's previously sorted. You're going to take a midpoint and check to see if that's the element that you want to find. If it is, you're done. If it's not, you could do a comparison to see if it's less than or greater than that element that you have. If it's less than, you go to the left. If it's greater than, you go to the right. and that kind of helps you divide out all these elements of the algorithm that you can then make it faster. We're going to run through it quickly with gophers. Our friends are back. And this time we're going to look for our gopher. And we could find him right in here, but if we wanted to use binary search, we essentially do the start and end of the array and find the midpoint. And here it's D. We do the D comparison with E. We know that E is after D, so we can split this into the left and right array. We know that E couldn't possibly be on the left array, so we just get to drop that. We move the low over to this E point, and we can now just search all of those three for our element that we're looking for. We do the same thing. The midpoint is the F. We know that E comes before, so it must be in this left array. We can now check it, and we do find, in fact, that E is where we expected it to be. The next part can be a little tricky. The question might be, well, what happens if your element isn't there? And essentially, oh, I have it written down in the question. If it isn't there, if you had something in between your E and your F, you would end up with the low incrementing, which would mean you now have this check of like high is less than low, which means you haven't found the element. And the same happens on the opposite side, high decrements, and you end up in this use case where you're like, there's nothing there that we're looking for. Here is the code that we are looking at for here. So we have the binary search. This is written a lot more like what you would literally find in a C++ programming book on algorithms, which I wanted to showcase because it's nice to know that you can just kind of follow these other books and like write it and go, and you're like, okay, I see what's happening. The main thing that's going on is I mentioned the high versus low. If it's lower, then we know it's not in the array, so we can return a -1. If high is greater than low, we calculate the midpoint, and we do the little checks. Have we already found it? If not, we need to know which direction to go. After that point, we can do the test. We've already seen this with Quicksort, so you can kind of just handle that and like run through all of your tests from your test tables to try that out. Same for benchmarking. And the last thing that I wanted to bring up, though, that's really fun fun for me, in binary searching is that you can do these stress tests. It's a lot like fuzzing, and essentially what we want to do now is like I have created these test tables, and I've put in all the variables that I think might come up. I've tried it sorted, I've tried it with duplicates, but how do I actually know that this program is working? And a lot of times if you have like an off by 1 error or maybe like a flipped like less than or greater than sign, it can take you a long time to notice that anything's going wrong, and a stress test can really help with that. So I wanted to give an example of how you could do that for binary search. In this second line, what we have here is we're creating a random number generator and using that to run 1,000 tests. So I have 1,000 here. You could run an empty for loop, and that would be an infinite loop. The only problem with that is if your code is working, it's going to run forever, so you will have to stop it yourself. But it's actually really fun because you can kind of watch and see if it might break. And then we go inside of here to actually create a new test for all of these different random intervals that we're creating. So the first thing we're doing is creating a numbers array. This is going to be an array that's either 1 element to 50 elements. And we're filling it in with something and incrementing. Every element in that array is going to be incrementing. So the first one will be between 0 and 100, first between 101 and 200. And we do that to make sure that our binary search is testing something sorted. After that, we select an X. That's the point that we're trying to find, and run it through this binary search. And this enables us to have like very large testing grounds that can find race cases or sections that you didn't test yourself that can be really tricky to find on your own. So with all of that covered, I just wanted to highlight these are some of the things that make me think writing algorithms is a lot more fun than your regular algorithms. And I would absolutely love to talk about it with you more if you're interested in this as well. This is my contact, and I would love to hear from you after the talk.